So before we start, are there any questions? So we have a defined goal today to complete the proof of Heine-Borel. Okay. Any questions before we start? Okay, very well. So our first goal today is, today's goal. So first is to show that the closed interval is compact in R. Any closed interval, but we will take 0, 1, is compact in R. And the second one is to show that the box, any closed box is compact in Rn. So let us say A1, B1 cross okay, good. All right, I should start recording this.
Recording in progress.
Okay, so that is our goal for today, what I have written over here. So a couple of questions. Compact in Rn or compactness in any space, you have to have the topology to speak of, a topology on that space to speak of compactness. So what is the topology that we use on Rn?
So any norm is fine, but I guess we could use infinity for.
Right. So the topology on Rn that is associated to a norm on that vector space, we have available for us the P norm for any P between 1 and infinity, inclusive of infinity. But we have checked that these are norms for P equal to 1, 2, and infinity. So we can use any one of them. The reason why we can use any one of them is because all three of them, we have seen that they are equivalent norms. So they give the same topology, right? So we will use P equal to infinity metric, but equivalent to equal to 1 and 2. Okay. All right. So before we get started, let's recall the definition of compact. So let's recall this. Recall a set K in some metric space is compact means. And let's write down the definition, not in terms of open sets of K, but in terms of open sets of X. Means, so what does it mean? Means the following. Come on, so this should be quick. We really do need this definition, and this definition needs to be at fingertips. So what does it mean?
Every finite cover, every open cover has a finite subcover.
Yeah, but every open cover, what does open cover mean here?
So I mean a family of open sets that contain X, K.
Okay, so let's make that statement better. A family of open sets. Remember, there are two space metric spaces here, K and X. So when you say open, you need to specify in which.
Open in, it is open in X.
Right. So our first definition was K should be any family of sets any family of open sets of K that covers K should contain a finite subcover. But then we saw that it is really equivalent to taking, it's okay if the family is that is given is of open sets in X. So means the following. If V alpha in alpha is in some index set is a family of open sets of X such that their union contains K, then there exists a finite subfamily V alpha 1 up to V alpha something, let us say K, such that V alpha 1. This itself is a cover, that is, this union contains K. So in words is to say any open cover of K contains a finite okay. All right, so let's just as a small warm-up, let us do the following. We have to get comfortable with using this definition without much thinking, that the definition should really be at fingertips. So let's so before we come to Heine-Borel, let's claim the following and prove it. Suppose I have a continuous function and K oops. So in other words, we are saying continuous image of a compact set is compact. All right. By the way, so it's compact where f of k is a subset
in
of
Y.
Y, right? But really, we also saw that compactness of a subset, when considered as a metric space in itself or as a subset of some larger metric space, they both really amount to the same thing. So f of k is compact. All right, let's prove this. So what do? We follow our rules. So let us say, let B alpha cover of what? So I need to show that a set is compact. So I need to start with its open cover, right? So I start with an open cover of what?
F of K.
Of f of k, correct? And for emphasis, by open sets V alpha of which space?
Y.
Of Y. So again, by the original definition, these should be open sets of f of k. But any open set of f of k is the intersection of some open set of Y with the subset f of k. Right? So it does not make any difference of Y. And I need to and the union of these, so by virtue of being open cover, we know that the union of these V alphas union of V alphas contains f of k. That's what it means to be a cover. Okay, and I need to extract a finite subcover. So what do I do?
Sir, we can look at the pre-images of each of the elements of the open cover and then.
So you see how the definition of continuity dovetails so nicely with this, or rather the characterization of continuity. What did we say? We saw in some detail that a function f is continuous. The definition of continuity between of a function between two metric spaces is by epsilon delta. But we saw that this is equivalent, f being continuous is equivalent to saying that inverse image of every open set of y under f is open in X. So the proof writes itself. Therefore, f inverse of V alpha by the way, all right, so let's erase this. Let's first do the set theory part. So union of f inverse of V alphas contains what? So I did ask you to check that the inverse image under any set function preserves unions. Just a straightforward thing. So f inverse of union of V alphas is, might as well write it down. Is the union of this. And what does it contain?
K.
Right. But really speaking, what I'm saying is I'm taking f inverse of both sides. So f inverse of f of k. And what can we say about f inverse of f of k? Is that equal to k?
Not necessarily, but it's a superset.
Right. So you see, there may be, so what are we saying? F of k. So these are all the images of points in k. And then I'm taking all the inverse images. So I could be catching other things, things other than k. See, for example, if f is the constant function, then what is f inverse of f of k? Come on, this is just set theory and I'm
Hello,
just...
sir.
Yes.
Sir, while taking the inverse image, shouldn't we intersect it with the range of the function?
Yeah, but okay. So let us write this again. So recall. This is just set theory. So let's write this over here. For any function g from S to T, and let us say I have a subset.
Excuse me, sir. F inverse of f of k contains k. Is that what you're saying?
Yes, that's what I'm saying. But let's first address the question that was asked. So the situation that I've written on the left is just set theoretic. So S is some set, T is some set, G is some set function, and A is a subset of T. So what is G inverse of A? By definition, it's just those elements X in S such that G of X is in A. So for example, to address your question, if the set capital A does not contain any image, can I take G inverse of that? Anything in the image? Yeah, I can perfectly well do that.
Yes, sir.
In that case, all that will happen is that G inverse of A will be the empty set. Okay, so it
Yes, sir.
makes perfect sense.
we only make sense of the fact that if g of x is an element of A, then then x is an element of S. But if
Right. So you got cut off there. But you see, we do not really even have to make that, make two separate cases. The definition takes care of all possible.
yes, sir. Yes, sir. Yes, sir.
Coming back to, so if f is the constant function, then what is f inverse of f of k? It's all of x, right? But it doesn't really matter. The point is that certainly the inverse images of f of k will contain all of k. So this contains k. Anyway, so what is the upshot? Thus, f inverse v alpha is an open cover of K. So I will just say open by continuity of F. Okay, and so now we are home free. So what do? Extract a finite subcover. So what do we have? F inverse of, let's say, V alpha 1 union F inverse of V alpha K contains K. So what is left to do?
The image of this finite cover.
Yeah, so just notice one thing. I can take f of both sides. So notice f of A union f of B is really the same as f of A union B. There is no issue over here. Because for a function for each input gives a unique output. So images of A union with images of B, where A and B are some subsets of the source of the domain. Then f of A union B is f of A union f of B. So take f of both sides. If you wish. And certainly, if one set contains another, then f of the first set contains f of the second set, right? Okay. So what is f of f inverse of V alpha 1? Okay, so this is bad. I should not have said this. Okay. So tell me what my mistake is. I'm going to erase this. Why is this a bad thing to say? Or misleading thing to say? What is f of f inverse of V alpha 1?
So it's a superset of V alpha 1.
No, think carefully.
V alpha 1 intersection range.
Yeah, so you see, if I take a subset of the codomain, if I take its inverse image and if I take the image, the result is contained in what I start with. But this is going to work in our advantage over here. So f of f inverse of V alpha 1 is contained in V alpha 1. All right, so let me write this down. This is certainly okay. F of f inverse of V alpha 1, f of f inverse of V alpha k. All of that contains f of k. And this is f of k, just to sort of be. Okay, let me not write this down. See, taking f of a union is the union of f of each set. Let me not write that down. But the point is f of f inverse of V alpha 1. What can I say about that? That is, how is that related to V alpha 1?
So it is contained in V alpha 1.
Correct. So V alpha 1 is bigger. So you see V alpha 1 contains f of f inverse of V alpha 1, and likewise for all other indices. So V1 union or V alpha 1 union up to V alpha k contains this. So you see, if you look at the first term and the last term, then we are done. Recall what we wanted to achieve. The V alphas covered f of k, and I wanted to find finitely many of them that covered f of k. So I have done that. Okay, so any questions on this? All right. So a small comment, I sort of went through this in detail, but something of this nature you should be able to do very quickly. So you need to reach a state of mind where something of this nature is something of this kind is almost like second nature. And you will get there with practice, even if you're not there now. Okay, so another question. So in the claim now, replace the word compact by sequentially compact. Is the statement true? That continuous image of a sequentially compact set is sequentially compact.
Yes, sir, for similar reasons.
Yes. Okay. So, so just remark. Also true that okay. So let me write this. That f of sequentially compact k is sequentially compact, and the proof is easy. So very quickly, so what does it mean to say that something is sequentially compact? Every sequence must have a convergent subsequence. So if I take a sequence in f of such k, then it will be of the type f of x1, f of x2, and so on, right? So what do I do? And I need to extract a sequentially extract a convergent subsequence. So of course I follow the same strategy. I simply look at the corresponding sequence x1, x2, and so on. This is a sequence in k. It must have a convergent subsequence. Take the images of this convergent images of entries of this convergent subsequence, and that will be convergent in the target because
F is continuous.
Right. So remember, that was another characterization of continuity, right? We did prove this, right, in class? I don't recall. Did we prove this?
Sir, it was an exercise.
It was an exercise. Okay. So let me just say easy. All right. So let's go back to our goal for today. By the way, also notice that this proof never used the metric. So this proof is really true for not just metric spaces x and y, but it's true for any topological spaces. Okay, so claim and yesterday we started with a proof. So we will come back to this proof, but let me just show you the nifty argument. So in the interest of time, I don't want to spend a whole lot of time on this. Okay, so how do I get started? I want to show that some set is compact. So what's the sentence that I should write down first if I'm just following my nose?
Given an open cover.
Right. So I first have to take an open cover. So let's do the same thing. Let V alpha in some index set. Okay, be a family of open sets in R covering so that means the union of all of these V alphas contains this closed interval. And I need to show that there is a finite subcover. Now this is the nifty definition. So I'm going to consider a set S. So these are going to be good points, right? So this is the set of points A in 0, 1, such that okay, so just look at this definition. So you might call the points of S to be good points. And what is our goal? So what is it that we want to show?
A equal to 1.
Okay. So you see,
So
A
1
is the
belongs
set
to
of
A.
all
1
points. Right. So one. So if I call the set S to be good points, let's say, just informally, then I want to show that 1 is good. So that is 1 is in S. Just look at the definition. This is a common strategy in math. Okay. If I want to show that some specific object satisfies some specific object A satisfies some property P, then I turn this around and I say, well, let's look at all the objects that satisfy property P. Then I will consider this set, some properties, how this set varies or whatever, the totality of, in order to, and this may be a good stepping stone to show that actually the desired thing also satisfies this property. Okay, so let's look at the properties of this set S. Any obvious properties that you see?
It's non-empty.
Okay, it's non-empty. All right, very good. Can you show me one point in S?
0 itself.
Yeah, so 0 itself is there. Of course, I have to then understand that notationally, the closed interval 0, 0 is the singleton 0, but that's okay, right? So closed interval from A to B is all those points X such that X is between A and B inclusive. So, okay, so this is non-empty. All right. But here is the sort of thing. So just take 2 points in the interval. So let me say what I have in mind to give you a hint. So what can I say? So Y is bigger than X, and both these closed intervals that I have written, they are subsets of the given closed interval. So what is the connection? Since X is less than Y, the enclosed interval on the left is contained in here, right? Okay, very obvious. Thus, so what can I say? What I'm trying to say is I'm comparing the membership of whether X is being good is related to Y being good.
So if Y is good, then X is good.
All right. So this is an utterly obvious statement. Just pause to see that it really is obvious. Because you see, if a finite number of the given family, if their union contains the entire interval from 0 to Y, then it certainly contains the subinterval from 0 to X. So let's write this down. Okay. So y is in S implies x is in S. What's the contrapositive?
X not in S implies.
So what we are saying is that if some point does not belong to, if some point is not good, then certainly nothing bigger than that can be good, right? Okay. All right, very good. So another thing, S is non-empty. So for example, 0 is in S and bounded. It's bounded on both sides, but in particular above. Why is it bounded above? Well, it's silly by construction because membership of S is restricted to the points in closed interval 0, 1, 3. Okay. All right. So here comes the thing. The first clever thing was to define the set S. Now the next slightly clever thing is to say that this set S, it's non-empty and it is bounded above. Therefore, the supremum exists. Therefore, it has a supremum. So let's take the supremum. So let U is equal to supremum. Okay, as I'm used to writing LUB. Same thing, no? Least upper bound. Okay. All right. So, of course, clearly, what is it that we want to show now in terms of this U? So, enough to show. So, in terms of this U, okay, what should be the value of this U? 1. 1. Will that be enough to show that? Will that be enough to show that 1 is good?
We have to also show that one is all element of S. Like
correct. So the way we will split this up is to show is that U is equal to 1 and U is also in S. Okay. And now we're almost home free. So just think about it for a moment.
There's an open ball at
Okay.
if it is not in.
So let me write this. Let me try to write this in the simplest possible way that I can. All right. So you see, the two bullet points together say the following. By the way, so far, just to sort of get just to get started, 0 is in this set of good points, but certainly there are other points also, correct? So why should any positive number be in S? Again, an easy point, but that needs to be stated. Why should any point other than 0 be in there?
There's an open ball at 0, so that contains something.
Right. So notice that what property the family V alpha has. It consists of open sets of the real line, and it covers the interval. That means that there is some V alpha containing 0. And since V alpha is open, therefore every point in that contains a ball around that point. So that means there is some V alpha that contains an interval minus epsilon to epsilon. So in particular, the point epsilon by 2 is good. In fact, any point less than epsilon, any point between 0 and epsilon is good, correct? We are going to need this, observation again. So I just said that about 0. Okay, but now suppose I take any point A between 0 and strictly less than u. Then what can you say about this?
There's a finite cover.
Well, yeah, there is a finite cover. Why is that?
Because you will
Right.
lose
So
the
there is a
supremum.
finite cover of what? So let's say this A is in S.
Yes, yes.
Right. Why is that?
Because U was the supremum, and like there's something between S, U and A that is also in S because of the definition of the supremum, and because that number is there, A must also be there.
All right. So let me write it in this fashion. Otherwise, looking at the first dot. So otherwise, I'm in this situation, right? So this is U. This is 0. And this is A. If A is not good, then what does the contrapositive state? Look at the IE part above. If A is not good, then everything above A is also not good. So therefore, this whole gulf of points between A and U, remember they're distinct points, then those are also not good. Then how could you be the supremum of this set of good points? Because points less than you are also not good. Otherwise, A itself would be an upper bound for S. Okay, very well. Now comes the clincher. What we did at 0, that little warm-up reasoning, what we said at 0, now we are going to do the exact same reasoning where see, the entire region from 0 to U is good, but I do not know whether U itself is good or not.
There is an open ball at U.
So what we did which is exactly what we did at 0, right? So we'll do the same thing. So the point is that, so as so U is going to be in some V beta, right? For some beta. And remember, V beta is open and U is in that. So I have some U minus epsilon to U plus epsilon is a subset of V beta. Okay, but that kills the single observation. The single stone kills both the birds. Remember what I wanted to show? I wanted to show that U itself is in S and U is equal to 1. Okay, so what gives now? Remember, every point less by the previous bullet point, every point less than U is in S, and I can take epsilon to be small enough so that this is also in 0, 1. You see, the epsilon might be very large because the V beta might be very large. Remember, I'm taking open sets of real line, but that's neither here nor there. So we can take epsilon to be small. And so U minus epsilon is in S. So what do I do now? So let us say some V alpha 1 union V alpha K contains 0 to U minus epsilon.
Then we also take the union with V beta. Say it is still fine.
So I take V alpha 1 union up to V alpha K. That will contain, oh, sorry. I will take the union of, okay, just excuse me. I will take the union of this with V beta. Notice the earlier union has taken me all the way up to U minus epsilon and including U minus epsilon. Now V beta allows me to take over from U minus epsilon onwards. The U minus epsilon itself is taken care of, right, earlier. So this will contain what?
That's a closed interval 0 to U.
Right. So in fact, so closed interval from 0 to U. So this is good. Okay, so let me just see if I can, yeah, okay. So U is in S, but more than that. But in fact,
Sir,
this,
if U is strictly less than 1, then it can't be the supremum. That's what we found with
exactly,
this.
right. So but you see, in fact, this set contains not just 0 to U, but it contains the closed interval from 0 to, well, I cannot say U plus epsilon, but I can say, for example, U plus epsilon by 2. So what this, is it clear? Because you see, I mean, the interval from U minus epsilon to U plus epsilon does contain U plus epsilon by 2, right? So what this is saying is that, so U equal to 1. Because otherwise, some U plus delta will also be in S, correct? Contradicting U is an upper bound. Contradicting choice of U, let me just say. Okay, contradicting that U is an upper bound. So that's it. I'm done. To appreciate this proof, so you should see if you can recreate this proof. Okay, it's the argument is simple, but it is very nice. You have to make the right definitions and have the right considerations. Did we actually construct a finite subcover? Was it a constructive proof? That is, when the open cover is given to you, did I actually show you how to extract a finite subcover?
Sir, we just used that it exists.
Yeah, so this was just existence, right? Can we make this constructive in some way? So if I give you a cover, then can you tell me, okay, take these sets? So we started in this direction last time. We said that we'll take 0, and then there will be some open set containing 0. That will allow you to go some distance into the interval. Take that distance. Then move slightly to the left, because the endpoint of that open interval, whatever V alpha you have taken containing 0, that will have some open interval containing 0. The endpoint of that open interval may not be in the open set you have taken. So move slightly to the left. and then start from there and continue. Then we said this was problematic because the lengths of these open intervals, they might keep shrinking so that when I add up, I may not reach 1. So you can think about whether this strategy can be salvaged. So let me write this down. Question. And while I'm writing this, you can think about whether I can be. Think about it for a moment. Can the strategy to actually construct, or let me not use the word construct, even better, extract of a given cover. So you see, what might you try to do when you're choosing this V alpha, you have some choice, no? Or you may have a choice. So when I'm taking the open set containing 0 and I want to cover some distance, maybe I should take not an arbitrary open set, but I can try to get the maximum mileage. So what should I try to do? Does the question make sense or not?
Yes, sir. We can take the largest set.
Okay, so largest in what sense? What does it mean to say the size of a set?
The difference in the endpoints should be the largest.
Right. But remember, V alpha is an arbitrary open set. So maybe what you want to do is you want to not consider the size of V alpha, but among all the V alphas that contain 0, take the one such that which contains the largest possible neighborhood of 0. But maybe even that is not good because you don't really care to what extent the set extends to the left. There might be a set from minus infinity to 0.1, but we don't want that. So you want to count the distance from 0 onwards. But you see, there are problems. So among all such possibilities, will there be a largest?
So we could try doing it in a different way. We could consider all the open sets that contain 0, and we could impose an order on all of them, which is the containment order. And so we could just take the largest based on that order.
Again, that will not work. Consider the possibilities where one of them is minus infinity to 0.1 and another one is from actually minus 1 to 2.
Right.
Right. So you do want to take some sort of rightward, the maximum rightward mileage that you get. Okay. So see if this idea can be made to work. I want to make a general comment that many times when you see a proof, the proof is so refined and so cleaned up and so elegant that it's difficult to see how people came up with it. Because you see, almost always the proof that you see in textbooks is not the proof that was written first, or at least it was not written in the same way, maybe. It has undergone a lot of refinement by several people thinking about it and making it the most elegant. Now, elegant proofs are very nice, but they're not always informative. So it's worthwhile to take a proof, to break it down, and maybe even try to come up with an uglier proof on your own to see what goes into it. Okay, anyway, so let's get a move on.
Sir?
Yes.
For this largest thing, could we so first our open cover, we'll just intersect it with a 0 and 1 so that we don't have any leftover things on either side. And then we'll change it slightly to like for each open set, we'll consider it's the union of open balls which make it, and we'll take that open cover. And then we will define largest as being the one with the difference of the endpoints of the interval being the largest. And we'll extract a finite subcover of that somehow. And then for each cover which came in our finite subcover, we'll just like extend it back to the original cover which was there in the original set. Oh, sorry, the original open set.
So see if you can make this work. All right.
Okay, sir.
Right. And then see the next thing is that when you think that you have an idea, the thing to do is to formulate your sentences carefully and write it down.
Yes, sir.
Okay. So in general, a good advice for everybody, not just you, for everybody, including me. Okay. So let's go on and do step 2, which is claim. So this closed box is compact in Rn. So recall we are going to use the p equal to infinity metric. So proof, and of course we are going to do induction on n. N is equal to 1 is done already. So I start as before. So and now I want to give this family a name, the alpha.
Hello, sir.
A cover of this box. Just 1 second. Cover of this set. Let's call this K. Let me just set this up, okay, and then we will come to questions. Be a cover of K by open sets in Rn. Okay, yes, go ahead, please.
Sir, the elements in the set are just n tuples, right, of real numbers, satisfying those inequalities.
Yes.
Okay, okay, sir.
Sir, I had to.
Yes.
I hate to just keep going after this, but I think I have a solution to the question.
No, let's not do that. Okay.
Sure.
Let's not do that. We can discuss this after the class.
Sure.
Okay. So we have a cover by open sets. I need to extract a finite subcover. We are saying induction, so let's split one off. So we will split the first slot off. So fix x in a1 comma b1 and consider this set x singleton in the first. So I'm saying consider the subset where the first slot is fixed to be x. So if I'm thinking of this as a box, then what I have done is, let's say this is a 3-dimensional box, n is equal to 3. Then what is this set? Oops, an comma bn. And let's just give this set a name. Let's call this C. So visually speaking, what is this? So imagine that this is a box, n equal to 3. What is this? What is this set X cross C? Visually speaking.
N is equal to 3.
N is equal to 3. And I have fixed some X between A1 and B1. This is just a slice, you see. If I'm taking a knife and cutting it at X coordinate X, this loaf, if you will, it's a loaf of bread. You are cutting it at X coordinate, a given X coordinate, then whatever cross section you get. So this is a slice. Okay, so why is this good now? This
We
slice
can
is
apply induction.
right. So what can we say about this slice? So X cross C. You sort of want to say that this slice is a one dimension down, correct? But is it really? I mean, formally speaking, this X cross C, it is like a box. So X cross C is like C, correct? Somehow. And what do we want to say about the set C itself? C is a subset of what?
R power n minus 1.
Right. And by induction, I can say that C is compact. But does it say that X cross C is compact?
Sir, I think we can continuously embed X cross C into C. And so that would imply, sorry, the other way around. Like we could show that there's a continuous map from C to X cross C. And since C is compact, X cross C must be compact.
Okay, so this was the reason why I did that. Of course, the result is, so X cross C is compact because, so C is compact by induction. Is compact because I have a map from, in fact, I can say I have a map from Rn minus 1 to Rn. What does it do? It takes any point P to which point? And maybe I'll put a bar
Ordered
over
pair P comma X.
or X comma P because I'm putting it on the first slot, right? Or let's even do this. Let's not be lazy over here. So let us say I have y2 up to yn goes to x y2 up to yn. And what can I say about this function?
Continuous.
Okay, why is this function continuous?
Because we can, it is each function in f of x1 is constant, which is continuous. F of x2 equal to x2, that is continuous, kind of like that.
Yeah, so we really have to do this more precisely. So exercise. Show that.
So we can use the L1 metric. I think that is enough. Because the first coordinate will just become 0, and that's why it'll just the same. So we can use delta as epsilon.
Okay, so you can use epsilon delta. All right, okay. But one thing that works very well with infinity metric is, see, with infinity metric, I can do this slot wise. And one thing that works well is sequences. Right? The sequence-wise definition and the ability, I mean, sequence-wise characterization of continuity, along with the ability to work slot by slot makes things easy. Anyway, so this function is continuous, and then what? The image of C is really so if I call this F, then F of C is really X cross C. Okay, so this is a minor point. Nonetheless, since we are proving things formally, every I needs to be dotted, every T needs to be crossed. Okay, so this is how we are going to do it. Now the proof actually starts. Okay.
Sir.
Yes.
So instead of using this continuous function thing, won't it have been easier to use the covering definition? Existence of finite cover for every open cover. Because there is just we add X to the tuple and its inclusion would have been easier.
How do I use induction? You see, I have to use the topology of C in Rn minus 1. That is, and the topology of X cross C in Rn. If I want to know that, if I want to see that, if I want to use, there has to be some bridge, you see.
Yes, sir. Yes, sir. Open in two separate sets.
I'm not saying that something like what you're saying will not work, but exactly what? A bridge has to be made between C and the slice X cross C.
Yes, sir.
All right. So, all right. So now for each point, for each P equal to X, Y2 up to Yn, in this slice. So I'm given an open cover of all of this box, right? All of the key, but I'm going to look only at the points in this slice. And for each one, I'm going to pick an open set. Pick open neighborhood, let us say V sub P in the given family. All right. So, so we need to start drawing pictures over here. All right. So this is what open interval from, closed interval from A1 to B1 is, and I have picked a point X here. And this remaining part, I'm going to think of this just represented by a vertical segment over here, because that's all I can draw on the page. In that case, so this is the box, entire box, and this is the slice. Okay, so this is X, and the vertical line in the middle is X cross C. So what I have done is that for every point here, I'm choosing an open neighborhood. An open neighborhood, which is from the given family. Now this open neighborhood may be something wild, but all I need is a ball around that point. Okay. Now I'm using the infinity matrix. So what are balls here? Come on. What are the balls in? The balls are just cubes, right? So basically the width of each one of them is going to be the same, right? So from the point P in each slot, you are going to go some distance in either direction, and well, let's call it epsilon. So every such, so this V sub P is going to contain X minus epsilon to X plus epsilon, open interval, cross Y2 minus epsilon, Y2 plus epsilon, Yn minus epsilon, Yn plus epsilon. Okay. And this point epsilon, this value epsilon really depends on, for some epsilon, sorry, I hate to do this, but epsilon P depending on P. So you see this epsilon is going to really depend on P, and I'm going to consider epsilons for different points P. That's why I wrote epsilon subscript P, but I do not want to write it in the expression above. Okay. All right. Now this one, let's give this a name to this. Let's call this W sub P. So the given point over here, this is what W sub P is, correct? A square in my given picture. Such a thing is contained in V sub P. Now what do we have? As I take this W sub P for each P in the vertical line, remember topologically, the vertical line is compact because it is just like C. The slice is compact. Around each point P of this slice, I have put an open ball. Therefore, by compactness of the slice X cross C, extract a finite subcover by W's. So what is this going to be? Some W1, W2, etc. So I'm going to write this WP1 union WP2 to WP, I shouldn't use N, so let's say K. This will contain what?
Sir, I think you mean VP1 because
No, I do not want to use VP1 because I really want to work with these boxes.
right.
Okay. I will come to V's later on. But you see, a finite subcover of the cover, oops, sorry. Of the cover WP. See, notice everything in that slice. I'm taking every single point in that slice, correct? And I'm putting around it a box WP. So since I've taken every point in that slice, all the WPs will cover the slice. And remember, the slice is compact, so I get to pick a finite subcover. So this is going to contain what? X cross C. But now comes the step on which the entire proof turns. So notice here I have put a slice. Here I have put a box, and at every point I take, I'm going to put a box around it. So here is a box. And there is a box like that around every point. But now I have taken a finite number of such boxes. So over here also there is some box. Over here there is some box. And all of these boxes cover the slice. But there are finitely many of them. So, but in fact, notice the following. In fact, the W's, so this entire thing covers not only X cross C, but you see it covers something bigger. Because you see in the first slot, around the point P1, P1 has, in the first slot of P1, I have X. And that is, there is going to be some width of the first box, which is epsilon. Let's say epsilon 1. Then the second box will have, dimension, width from the center. That is, the total width will be 2 epsilon. But let's look at the epsilon. So the first one will go from epsilon, will have plus minus epsilon 1. The second one will have plus minus epsilon 2, and so on. But if I have only a finite number of boxes, that means that the total width as I go vertically around the slice, if I take the union of all of these boxes, each one of these boxes will contain width equal to the minimum of all the epsilons. So let me write this down, equal to X minus epsilon, X plus epsilon, where epsilon is equal to the minimum of epsilon P1 up to epsilon Pk. is that around each point X, I have put, so for each point X, I have the slice, but more than the slice, I'm actually covering a tube by means of a finite number of W's. So what is the upshot? So now I go to V's, VP1 union VP2 up to VPK. Oops, sorry. That was this contains WP1 because each of the V's contains the boxes, right? And this contains the tube X minus epsilon to X plus epsilon. Let's see. Okay. So over here, for example, the smallest of, so of the 4 boxes that I've drawn, which one is the smallest? Which one is going to give me the smallest epsilon? Going from top to bottom, first, second, third, fourth, which one is the smallest width?
First one.
First one, right? So this one, and I'm going to get the corresponding width over here. So all right. So what now? You see, around every point I have taken a tube that is covered by finitely many of the given V's. So now what do I do? See, I have used compactness in the C part, but I will use compactness in the first slot. Now is X minus epsilon, X plus epsilon. As X varies. So until now, X was fixed. X minus epsilon, X plus epsilon give an open cover. A1, B1. So I find a finite subcover and take the union of all the respective V's. But I should have really set up my notation here. So let me write down here. So you see another thing. Unfortunately, there is no way around this. But this notation, you see the epsilon that I have chosen, the minimum of the epsilon P1 up to epsilon Pk, that epsilon also depends on X, right? So I should really write this epsilon to be epsilon sub X or something like that. And now this and this family, let me write down the notation over here. Let F sub X be the family VP1 up to VPK. Extract a finite by compactness of the closed interval. And let's call this X1. Oops, okay, we are out of time. Let me just try to finish quickly. x1 minus epsilon x1 to x1 plus epsilon x1 up to x. Now I need to use a different letter, xl minus epsilon xl, xl plus epsilon xl. Okay. Can you finish the proof now? I'm sorry that the notation has become a little hairy. The idea is quite simple using these tubes, but there is no way around the fact that you have to give names to many things. So to recap and to finish, what did I do? For each point X, I found a finite subcover of a tube around X, consisting of some bunch of V's, right? And that family of V's is what I called F sub X. So you see this F sub X is a finite subcover of a tube around X. So how do I find a finite subcover of the entire, a finite number of V's that cover the entire box K? All right, so the reason for this silence is not because what is being done is difficult, but because most likely you're just lost in the notation.
So
So
only subset cross C will be the open cover of entire cube.
No, remember the subcover has to be from the given family.
So
we
all
can take
the intervals that you, the finite subcover of E1 comma B1 that we've created, we can just take a cross C of all of them, and that will cover the entire space by definition.
No, so see, you are not going to take cross because you have to finally you have to take sets from the given family.
Yes, sir. I know. I was asking you to take x1 minus in the epsilon x1 comma x1 plus epsilon x1 cross C, and that is part of the family by the.
Yes, but I have in fact given a name to the requisite family. Just see.
As fx. Okay.
F sub x1.
F sub x1. Yeah.
So this F sub x1 is a collection of V's from the is a subset of the given collection that covers the tube around x1. And I have taken a finite number of such tubes that will cover the entire thing. So the F sub x1, F sub x2, union up to F sub xl is a finite subcover of A1 comma B1 cross C, which is all of K.
Sir, could you just once repeat what are x1, x2, xl?
Correct. So notice what is happening. In the given picture, I first fixed an X, then I took a slice, X cross this remaining part of the box. And I covered the slice with a finite number of sets from the given family. So the slice X cross C is covered by VP1 up to VPK. But I observed that actually this finite family, VP1 up to VPK, it covers not just the slice, but an entire tube around the slice. So not just the singleton X cross the vertical C, but actually an entire open interval X minus epsilon to X plus epsilon cross C. So what is happening now is that the entire space is thought of not as, see, the entire space is covered by the slices, correct? At each point X, I take the slice. But what I'm doing now is that the entire space is also covered by tubes. Around each point X between A1 and B1, I have found an interval from X minus epsilon to X plus epsilon, such that the tube X minus epsilon to X plus epsilon cross C is covered by a finite number of sets in the given family. Now, what I showed is that a finite number of such tubes cover the entire set, because a finite number of the intervals from X minus epsilon to X plus epsilon, they cover the entire interval from A1 to B1. So you see, I'm using compactness twice. Once for induction to extract this finite subfamily of W's and therefore of the respective V's, and then compactness of the closed interval from A1 to B1.
Yes, sir, I understood.
Okay. See, the proof is not difficult, but it is one of those proofs where you have to keep track of notation. So what I would suggest is that the basic idea of the proof is to use compactness both for C, that is the part from A2, B2 up to A and Bn, the product, and then separately use compactness in the remaining slot, the first slot. Okay. So try to recreate this proof on your own. That's the way in which maybe that is the best way in which you can try to understand it. Just try to recreate the proof. Anyway, so I'm way out of time, so we should stop now.
Recording stopped.
Again, this is a typical argument. You should see the similarity of this argument with what we did earlier. Is that yesterday, I mean, in the previous class, we showed that when we showed that every compact set is closed in a metric space. What did we do? We put balls around distinct points, one inside K and one outside K. Then I took a finite subcover, and for the balls around K, for the balls inside K, I took their union. For the balls around points inside K, I took their union. And for the balls that were outside, I took the corresponding points. I took their intersection, right? Sorry, I'm saying this very badly.
After taking a finite subcover,
right. So exactly, after taking a finite subcover, intersections work well. Because finite intersection of open sets still stays open. You see, exactly the same idea is used over here. Except here the intersection is very nice, because what I'm doing is I'm taking intersection of open intervals around a point. So intersection of a finite number of open intervals around a point will simply be the, and they all are centered at the point. So what is the intersection? You just simply have to take the smallest width. That's what happened over here. So when I took the min, that's what is happening. I'm taking the intersection. So as an exercise, you can try to do the following. Exercise. Let us say that X and Y are topological spaces. Suppose K and L are compact subsets Okay. Let's see. Respectively of X and Y. Then what should be the proof? What's the claim? So X is like R, Y is like R, and K and L are like closed intervals. So what is a box in R2? It's closed interval, cross closed interval, right? So what should be the claim analogously?
K cross L is compact.
But this sort of brings in a question, right? Compact in what? You have to have a topology.
In X cross Y.
Yeah, but X cross Y is a very nice as a set. What is its topology? That's a question that we need to address now. So in Rn, you see, we did not really need to address this question because we didn't really think of R2, for example, as R cross R. We just thought of it as R2 and we gave a topology to it. And somehow, you see, this infinity norm is nice because it allows us to just deal with it slot by slot. No? So I have to, but I do not have, but over here, I cannot really, X and Y may not have any norm or anything. So I have to see what kind of topology to give. So I will just say where open sets of X cross Y are open set of X cross open set of Y. At this point, you should really make me pause.
Will this satisfy the axioms of a topology? I guess we need to see.
Okay, so will it? Okay, so there are two axioms to check. Is this collection closed under finite intersection? So U1 cross V1 intersection U2 cross V2. What is that?
So U1 intersection U2 cross U1 intersection U2.
Yeah, this works, right? Because what does it mean to take intersection of two things? You have to have both conditions. So the first one is saying first slot must be in U1 and second slot must be in V1, and first slot must be in U2 and second slot must be in V2. That's really the same thing as saying first slot must be in U1 intersection U2 and likewise in the second slot. So intersection works well, but union just does not, you see. I mean, you can just see this in a picture. If I take open interval in R cross open interval in R, then that is going to give me the interior of a box in R2. Right? Is the union of these is an arbitrary union of these? Okay, so I think maybe in R2 this will work. But in general, there is no reason for this to work. So what we have to say is that unions of such sets. So that is the topology on X cross Y. No, sorry, what am I saying? That's just dumb. You see here, here's an example. Just look in R2. If I take, and here the boxes are open, all right. So if I take union of two such things, it is not a Cartesian product. Do you see this? It's not a Cartesian product of two sets. because, for example, this is not a Cartesian product. Okay, anyway, so yeah, so sorry, this proof just somehow may have felt very hairy, but it really is not. So please try to go over it by yourself and try to reconstruct it. But for now, we should just stop unless you have some questions. So by now, we are more or less done with the topology of Rn part. Okay, we may have a few things to sort of loose ends to gather, but we will just now start with our proper brief that is given to us, which is to do calculus in Rn. So I think in the next class, we'll be able to define the derivative. And in order to do this, you really need to know your basic linear algebra. Okay, so any questions?
Yes, sir. I had questions about two of the exercises you've given after classes. Sir, one of them was the one you gave last time about if we have two compact topological spaces. If we have a topological space which is compact and Hausdorff, and we have two compact subspaces of that.
Or closed, so right? Which is the same.
Yeah. Yes, sir. Yeah.
Right.
So that we can find open sets around, disjoint open sets around them. So,
yes.
Is the compact, do we need that the ambient space is compact for that?
We don't need it, but we will write. Okay. See, that is the thing. Because the way I formulated it in class, so in notes I changed with the ones that I uploaded. I changed the hypothesis to the sets K and L being closed.
Okay.
And then you see, if I don't have the ambient space compact, then why should these K and L be compact, right? That is how it is normally done. Okay. So, but you are right. If those two sets themselves are, compact, you probably don't. I think the proof will just go through without the ambient space being.
Yes, sir. Okay, sir.
Without the ambient space being compact. Yes.
Okay, sir.
Yeah.
That was one question. And then another one was about the characterization of continuity that we looked at. That is, if f is continuous if and only if f of s bar is a subset of like the image of f.
Let me write this down.
Yes.
So x to y f is continuous if and only if f of S closure is contained in f of s closure.
Yes, sir. So I'm not sure if the backward direction holds. I think if x and y are both R, we can do we can define f piecewise as from, let's say, open 0 to open 1, open 0 to closed 1. It can be f of x is equal to x, and then from
okay, so let me just write this down. So what is your x?
So okay, x is say open 0 to 2.
Okay.
And f is on open 0 to open 0 to, let's say, closed 1. F of x is equal to x.
So sorry, okay, open, let me just get this right. F of x equal to x for x in 0 to, okay.
And then for x in open 1 to open 2, it is 2 minus x.
Okay, so I just need to draw a picture of this. So this is just that. Okay. And then, okay, so you just have this function, all right? And then you are going to go down like this, right?
Oh,
And then this point is not included. No, isn't
sorry,
that what
sir.
you want to do?
Uh, I, I wanted to, I think I got the function wrong. I wanted to take the same line, y is equal to x, and just flip it in 0 to 2. So it should be,
Okay, so this is what you want to do. Okay, so in fact, let's. So this is what you want to do. Is that what you want?
oh, I think this will work also. Or I think this is also a counterexample.
No, the point is, do you want the function to be continuous or not?
No, I don't want the function to be continuous.
Okay, so the earlier one was not. The earlier one was continuous. Okay.
Yes, sir. Yeah.
Okay. So you are claiming that this one will satisfy f of s bar is in the for every single possible subset. So this is not 2 minus x. It's whatever it works out to be. So what is it going to be? It's going to be x minus 1, no?
Yes, sir. So now
Right.
I think I might have made a mistake. I don't know if I consider this for every possible subset.
Right. You see, so
I think I might need to think about this again. I
right.
think, yeah.
Think about it. So
Sir, will our last proof work if the cross section is varying? Like,
okay. So by the way, so there is a comment. So it says that for backward direction, we can show that F inverse of closed set is closed. And you see, this sort of is indicated, right? In the sense that this is saying something about closures. So those are closed sets, and we do have some understanding of continuity in terms of closed sets. So
Yes, sir. I think I got very, very confused. I think what happened was I did not consider all subsets. And so I thought I had a counterexample, but then I realized that and I forgot that I did that. So I'm sorry, sir. Thank you. Yeah.
no issue. So, okay. All right. So, so I'm just going to put a question mark over here. Yes. Okay. So let's go back. Let's go back to this proof. Right. So which part? So what part of it do you want to discuss?
no, sir. Like, if we took a slice, right? So if the cross section of the
Yes.
slice was changing, will the same proof work to prove that that set is compact?
No. What do you mean cross section is changing? I do
mean,
not understand.
it is not a cube, like the cross section. We're taking the slices along the first coordinate, and that cross section is changing. Like the area, it's a rectangular set, but it's changing.
Right.
I want to like know whether we are using this proof.
Do you mean to say it is changing? You mean the shape of it is changing? Is that what you mean to say?
No, like it's increasing. Maybe like it's a rectangle, but it's a square. It's a rectangle, but it's increasing or decreasing. It's changing smoothly. Oh, okay, sir. Okay.
I do
There
not.
are okay, so yeah.
There are
I
do not understand the. I do not understand the nature of the question. I mean, what?
Yeah. No, there are additional assumptions. So yeah, regarding how it is changing and all that. Okay. No, it's not a good question.
I mean, the only thing that is being used over here is that each one of them. So, what is being used over here? We are using the fact that I'm using this infinity metric is being used because this means that the balls really just are Cartesian products. That allows, that makes things easy. And then we are using that in the first slot. I just have open intervals, and I have a finite number of them, so I can just take their intersection.
I mean, in the last step, we are doing something, right? Like we are only considering the sequences in the first coordinate, and then the last step, like we are just going from that coordinate to all the coordinates. So isn't that working because it's always a constant?
No, what is always a constant?
The rest of the coordinates. Like
No, it is the rest of the coordinates, in fact, are not constant. The rest of the coordinates, in fact, can be arbitrary. See, so think about it carefully. You see, it's a Cartesian product. So that means that the first slot and the second slot, they can be chosen independently of each other. You have to think this through carefully.
Oh, okay, sir. Okay,
right?
We need just
you see what is a tube? The tube is a Cartesian product of two things. That means that all possibilities in the first slot have to work with all possibilities in the second slot.
Okay, sir.
Right? Yeah, so this proof is worth meditating on for some time if you do not understand what's going on. And perhaps what you can do is to untangle, it may be worthwhile. See, really speaking, this exercise that I have given you, you will do this in your topology course, okay, pretty early on. But perhaps to disentangle the metric space aspect of it or the infinity metric aspect of it from the basic procedure, the basic construction that we are doing, it may be worthwhile to do this exercise in the context of topological spaces. Then you will see what is going on. The part where we took minimum, what will that be replaced by? That will be replaced by the simple assertion that intersection of a finite number of open sets is still open. Try it. Okay. I mean, you will still have the same V's, but what will take place of the W's? And I'm doing this only 2 slots, right? So I don't have n slots. I have only 2 slots. What will take the place of W's is still going to be a Cartesian product, you see, because arbitrary open sets in X cross Y are unions of open cross open. So if I'm given some point in an open set, then it will have a neighborhood of the type open cross open. So the definitions for an arbitrary topological space are made in such a way that the exact same strategy is going to work. You're still going to take slices, and you're still going to have this tube lemma. The fact that not only can any slice be covered by a finite number of sets from the given family, but this finite number of sets will actually cover a tube, not just a slice. So maybe this is worth writing, and I'll write this down over here. not just the slice. That's the key. That really is the key point of the. And then if I take the widths of all of these tubes that I'm getting around each point, then all those widths, from that I can extract a finite number of tubes, because the finite number of widths will cover the first coordinate, all possibilities in the first coordinate. So I can take the associated finite number of tubes to get the finite cover that I want. Okay, so anything else? All right, so now that we have more or less finished with the topology, a first homework will come. So be ready, and it will really be just essentially stuff that we have, that I've exercises that I've assigned in class, or small exercises. So, okay, so if there is nothing else, then let's stop and we will continue on Monday.
Thank you,
Thank you,
sir.
sir.
All right, bye everyone.